Dear students, welcome to our class. Welcome to the class of higher physics, the most easiest and the finest way to learn concepts of physics. Today I am going to teach you Ampere's Circuital law. Just like you have seen in electrostatics that Gauss's law is the alternative form of Coulomb's law, in similar way in magnetism, Ampere's Circuital law is the alternative form of Biot-Savart's law. In the first part, we have discussed about Biot-Savart's law, what Biot-Savart's law is, how to use Biot-Savart's law for calculation of magnetic field around current carrying conductors. Okay, so I will repeat the equation that we use for calculation of magnetic field due to a current carrying conductor by means of Biot-Savart's law. That is dB, small amount of magnetic field. For small length element, it is mu naught by 4 pi I dl sine of theta divided by r square. This is the equation for Biot-Savart's law, and this we use for calculation of magnetic field due to current carrying conductors. Okay, so there is the alternative form of this very law that we call as Ampere's Circuital law. One more important law in magnetostatics, we call that as Ampere's Circuital law. Okay, तो आज हम बात करेंगे Ampere's Circuital law की और its applications के बारे में आज हम पढ़ने वाले हैं. Okay, now Ampere's Circuital law, the law which gives the relationship between magnetic field and electric current. We will discuss that. Suppose we have a current carrying conductor carrying current I in this direction. See, from X to Y there is the flow of current. Okay, so around this current carrying conductor there will be magnetic field. Okay, and we know that we represent that magnetic field by the imaginary lines called as magnetic field lines. And here, around a straight current carrying conductor, the magnetic field lines are always in terms of concentric circles, as shown here. So magnetic field lines around a straight current carrying conductor are always in terms of concentric rings, as shown in this figure. Okay, now how to calculate the magnetic field for any closed path? We will make use of a law called as Ampere's Circuital law, which states that the line integral of the magnetic field around any closed path. Suppose this is the current carrying conductor. It is carrying current I from X to Y direction. Suppose we will take a circle out of these concentric rings. We will take a ring here. Okay, suppose this ring is having, a circle is having some radius, say R. Ampere's Circuital law states that the magnetic field and the line integral of the magnetic field around this closed path, we represent that by line integral of magnetic field, and this represents closed path. B dot dl is equal to the absolute permeability times, because this conductor is in free space. We will make use of here absolute permeability, that we call as permeability of free space, and we denote that by mu naught times the current, and the current is I, so it is mu naught times current I. So what Ampere's Circuital law states that the magnetic field and the line integral of magnetic field around any closed path in free space is always equal to the absolute permeability times the net current enclosed by the path. And this statement we call as Ampere's Circuital law. Means इस करंट कैरिंग कंडक्टर में से जो करंट पास होता है उसकी वजह से जो मैग्नेटिक फील्ड होगा वो मैग्नेटिक फील्ड को हम रिप्रेजेंट करेंगे इन टर्म्स ऑफ कंसेंट्रिक रिंग्स. Okay, these are called as magnetic field lines. We use these lines for representation of magnetic field. It's an imaginary concept. Okay, so here this closed path, the magnetic field, and the line integral of magnetic field around this very closed path in free space is equal to the absolute permeability times the net current enclosed by the path. Okay, the statement we call as Ampere's Circuital law statement. Now let's prove this Ampere's Circuital law. We will prove this law on the basis of Biot-Savart's law. Since we have here a straight current carrying conductor, and we have discussed in the first application of Biot-Savart's law that the magnetic field around a straight current carrying conductor at any point is equal to B equal mu naught by 4 pi twice I by x, where x is the distance of point P from the center of this current carrying straight conductor. Okay, so let we prove this line integral of B dot dl equal to mu naught I, means let we prove Ampere Second Law statement on the basis of Biot-Savart's law. Since here we have a straight current carrying conductor, suppose around this straight current carrying conductor there is magnetic field at this very point P, which is at some distance r from the center of this current carrying conductor. Okay, so इस वाले point पे जो magnetic field होगा by means of Biot-Savart's law, that magnetic field B will be equal to this value mu naught by 4 pi twice I by x. हमने ये prove किया in the first application of Biot-Savart's law. Okay, so here I can write therefore जो magnetic field है due to this straight current carrying conductor according to Biot-Savart's law, that is B is equal mu naught by 4 pi twice I by x, और x के बदले यहाँ पे distance क्या है, that is this radius of this path, that is r. Okay, so B equal to mu naught by 4 pi twice I by x. This mu naught by 4 pi is the value of k, constant, I is the current, and x is the distance of point P from the straight conductor, and here the distance is r. So I can write B equal to mu naught by 4 pi twice I by r. Okay, so now we have to prove line integral of B dot dl equal to mu naught times current I. So here we have a straight current carrying conductor. See this, it is a straight current carrying conductor. Around this we have magnetic field. If at this very point magnetic field is this, it is the magnitude. But about the direction of this magnetic field, that direction we can calculate, and we can go for that by means of a rule called as right hand thumb rule. Okay, so what right hand thumb rule is, we have a straight current carrying conductor. It says that imagine you have, suppose this is a conductor, a straight conductor. Imagine you have a straight conductor in your hand, in your right hand. Okay, and keep this conductor in such a way that the thumb of your right hand points in the direction of the current. Means अगर current की direction यहाँ से यहाँ है, means from this point x, this point y, it is going from this point to that point. Okay, current is in the upward direction, and you are taking this conductor, imagine you are taking this conductor into your right hand so that thumb points in the direction of the current. At that time, right hand thumb rule gives the direction of magnetic field. It says that these fingers which are encircling this, and which are curved around this current carrying conductor, these curved fingers give us the direction of the magnetic field. It is similar here. You have a straight current carrying conductor. Okay, the thumb is pointing in the direction of the conductor and in the direction of the current. These curved fingers will give the direction of the magnetic field. So at this very time, if the current is going from x to y, the direction of current will be in this way. Means the direction of magnetic field, not current. The direction of magnetic field will be in the anti-clockwise direction, as shown here. This is magnetic field direction, and this direction we get by a rule called as right hand thumb rule. Okay, or the direction of current at this very point, magnetic field, it will be always tangent to that point. So this is magnetic field direction, and this is given by right hand thumb rule. Okay, so now this is the direction of magnetic field. This direction is given by right hand thumb rule. At this very point, direction is tangent to that, as shown here, and the magnitude is B equal to mu naught by 4 pi twice I divided by r. Okay, so now we are going to prove this statement. I will take now, अगर हम यहाँ पे एक small element लेते हैं, see at this very point we will take a small element whose length is dl, and dl vector is the current element. Okay, at this very time the current element and B, means B and dl, will be in the same direction, And when two vectors are in the same direction, their angle is always 0 degree. Okay, so for this small element, I will take the magnetic field along this small element, that is B dot dl, equal B dot dl. You have seen in class 11th vector scalar product A dot B, it is A B cos of theta. So B dot dl will be equal B dl cos of theta, and that is equal to B dl cos theta के बदले B और dl एक ही डायरेक्शन में है, उनके दरमियान का जो एंगल रहेगा वो 0 रहेगा. And what is cos 0? It is equal to 1. So it is B dot dl equal to B dl into 1, that is B dot dl equal to B dl. And this is the magnetic field for this very small part, this very small length element having length as dl. Okay, now suppose there is not only single element, there are number of such elements, say this like that. Okay, so there are number of such small current elements. Okay, so to calculate the magnetic field for that closed loop, we will integrate this equation for closed path. Therefore, integral over closed path, it is B dot dl equal to integral over closed path B dl. And this is equal, B is constant here. At every point on this very ring, the magnetic field is constant. Its value comes out to be mu naught by 4 pi twice I by r. And you can take B out of the integral. It's here integral of dl. So that is B into, what is integral of dl? Integral of dl. So ये is dl is small element. The sum of all these small elements will give the total length of this very loop, and that total length will be circumference. And what is the circumference of that? It is 2 pi r. Okay, so line integral of B dot dl equal to B into 2 pi r. Okay, so this will be line integral of B dot dl around the closed path equal to B is here, and the value of B we have calculated, it is mu naught by 4 pi twice I divided by r multiplied by 2 pi r. Okay, so B का जो value हमने calculate किया है by Biot-Savart's law around a straight current carrying conductor around any point, you will have the value of magnetic field equal to mu naught by 4 pi twice I by r, and here use this value here, B के बदले ये value into 2 pi r. R and R will cancel, pi and pi will, 2 2s are 4, 4 and 4 will, and this comes out to be, यहाँ बचेगा तो mu naught और यहाँ बचेगा क्या, R. So this line integral over closed path of the magnetic field comes out to be absolute permeability times the current, and this B dot dl over closed path line integral of that equal to mu naught I. We call that statement of Ampere Second Law, and this law we use for calculation of magnetic field around the current carrying conductor. Now let me use Ampere Second Law for calculation of magnetic field due to a straight current carrying conductor. The first application of Ampere Second Law, calculation of magnetic field due to a straight current carrying conductor. Okay, suppose we have a current carrying conductor carrying current I in this direction, and we know that by means of this right hand thumb rule, the magnetic field direction will be always in this way. This direction of magnetic field around a straight current carrying conductor when the current flows in this direction. If the current flows in this very direction, then the magnetic field direction will be in the clockwise direction like this. Okay, so हम calculate करते हैं magnetic field due to a straight current carrying conductor. Okay, so let's have a straight current carrying conductor. This is the magnetic field around the straight current carrying conductor. Suppose we will take a point, say point P, at which we will calculate the magnetic field, and suppose this point P is at some distance r from the current carrying conductor. Okay, now here the direction will be always tangent to this one, and that is the direction of magnetic field B. Okay, if you take the small element here having length as dl, then dl and b will be in the same direction, and the angle between two dl and b vector will be always 0 degree. Okay, so let me calculate magnetic field at this very point due to straight current carrying conductor, but by means of Ampere Circuital law. So we know that according to Ampere Circuital law, line integral of magnetic field for the closed path B dot dl equal absolute permeability times the current. It is mu naught I, and you know the value of mu naught. It is 4 pi into 10 raised power minus 7 Tesla meter per ampere. Okay, and I is the current flowing through the conductor. And we can write this B dot dl equal to B dl cos of theta equal to mu naught times current I. Because A dot B equal to AB cos theta, B dot dl will be equal to B dl cos of theta. So it is line integral over closed path B dl. What is angle between B and dl? It is 0, so it is cos 0 degree equal to mu naught times current. And that is line integral over closed path B dl cos 0 is 1 equal to mu naught times current. Okay, so you can write it is line integral over closed path B dl into 1, that is B dl, equal to mu naught times current. And we know that this B magnetic field at any point is constant. You can take this B out of this integral, therefore you can write B into integral of dl equal to mu naught times current I. Or we can write B is equal, what's integral of dl? It is the total length of this very path, and that is the circumference of that, and that is equal to 2 pi r equal to mu naught times current. Okay, you have to calculate magnetic field, therefore magnetic field B is equal to 2 pi r, यहाँ multiplied है तो वहाँ divide होगा, it is mu naught times current divided by 2 pi r. That is magnetic field due to straight current carrying conductor, and we have shown B equal to mu naught I by 2 pi r using Ampere Circuital law. हमने already इससे पहले भी ये प्रूव किया है, but on the basis of Biot-Savart's law that B is equal mu naught by 4 pi twice I by r. Okay, here 2 and 2 will cancel. It is B equal mu naught, यहाँ बचेगा mu naught I divided by 2 pi r. This value is same whether you will calculate the magnetic field due to a straight current carrying conductor on the basis of Ampere Circuital law or using Biot-Savart's law. The value comes out to be B equal to mu naught I by 2 pi r. Here it is mu naught I divided by 2 pi r. This is the first application of Ampere Circuital law, how to calculate magnetic field due to a straight current carrying conductor. Okay, thank you.